This week, we are going to continue discussing linear models. So here is where we are. We are on week 5, and we are discussing a concept called neuron. Okay, so this is a single layer perceptron. We will introduce another linear model, and we will introduce stochastic gradient descent, SGD, for training our models. Okay. All right. So the plan is like this. So we will discuss 3 main topics. Okay. So in the beginning, we will learn another linear model called log linear models. So that's in addition to perceptron and SVM, right, we have learned. And second part, we will learn SGD. So it's an optimization algorithm, which we will see for both linear models and neural networks. And third, we will discuss the neuron. Okay, I will show you that SVM, perceptron, and log linear models, they are all just one model, okay, a single layer perceptron or a neuron. And then if we have time, okay, we will discuss how to combine the strengths of multiple models. First, let's look at log linear models. So before I introduce this model, let's review, okay, the linear models we've learned. We've learned one generative model, which is naive Bayes, right? And 2 discriminative models, which are SVM and perceptron. So if the feature vector, okay, consists of 2 feature templates. One is C, another is WC, right? So these 3 models can actually be unified, right? So on the left is the feature vector, okay, which contains all the possible feature instances. And on the right are the parameter vectors of the 3 models. And you will see that for naive Bayes, every model parameter is already predefined, right? So corresponding to C is log PC. Corresponding to number of W and C is log PW given C, all right? But for SVM and perceptron, we only make sure that these parameter vectors are as long as the feature vectors. And then we start off training them using data, right? Okay, so for these linear models, we are all calculating the score using theta.phi, right? So for multi-class classification, we learned that we need to extract features over x and y. So phi xy dot theta is the score, right? And we find the y that has the highest score as the output. All right. So the advantage of SVM and perceptron over log linear models is that they support arbitrary feature definition, as I showed you last week, right? We can use C, WC, BIC, every kind of feature we can define. Right? We don't worry about generating every word only once. But naive Bayes also has an advantage, which is that the output is a probability, right? So for SVM and perceptron, the output is just a score, okay? Maybe 10,000, maybe minus 100. But you don't know what they mean. You only have the relative score difference, right? Meaning one is better than another. But you don't know the meaning of absolute scores. But for naive Bayes, you know, the score is the probability, right? So the probability of the input and output together is 0.5, right? So you get an idea, right, what it means, right? Okay. So the idea is, can we build a probabilistic discriminative model, right? So can we build a discriminative model that allows us to use features, right? Feature dot parameter to calculate scores, right? And then the score becomes a probability. That's the question, right? That's what we want. So how can we do that? Okay, we got an inspiration from naive Bayes. You know, naive Bayes models calculates PEC given D as the joint probability of C and D. Further as the sum of, you know, log PW given C and log PC. Right? So the logarithm form of naive Bayes is a linear model, right? So the log score, the log probability is linear, right? So we got the original probability as a product, but the logarithm is a sum. Inspired by this, okay? So when we have theta dot phi as the score, so could we have an exponential function, okay, that turns this into a probability? So that's the basic idea, okay? So we still have a linear model, okay? We have theta monoparameter and phi. The phi definition is the same as SVM, okay? But theta dot phi is from minus infinity to infinity, right? We want to make it an exponential function over theta dot phi so that the result is something between 0 and 1, okay? What functions can allow us to do that? Okay, so a very simple idea is, all right, let's first turn theta dot phi, right, into e to the power of theta dot phi, exponential function. But that's still ranging between minus infinity to infinity, right? How do we turn that into a probability? All right, you say for every class, right, the score is e to the power of theta dot phi. So why don't we just normalize them? Okay, we use, okay, the sum of all possible class labels, e to the power of theta dot phi, okay, to divide the score of every class label, now resulting in this equation, you know. That's just a normalization, right? Normalized over the score of every class label. And that will be, that will lead to the fact that the score of every class label adds up to something between 0 and 1, right? And because it's an exponential function, you know, it's not negative. So if something non-negative will sum up to 1, then everything will be between 0 and 1, right? So this is a function. And the function here, we call it a soft max function, okay? So we just give it a name, but this name is just as what I write here, all right? So a soft max function is an exponential function, okay? Normalized over a set of numbers. You can see more details in the textbook. All right. So this is for multi-class classification, you know. We have theta dot phi x, y, okay? But for binary classification, when we discussed them last week, we say, okay, you could do this, but you could do something simpler by extracting a feature representation of the input only, right? Phi x. So how do we turn a score of phi x into something between 0 and 1? Okay, now remember for SVM, we have phi x and we have theta dot phi as the score, right? And this is something between minus infinity and positive infinity, right? And we say if this something is more than 0, then we take the positive class. If this something is less than 0, we take the negative class, right? That's what we did for perceptron. So theta dot phi x is the score. How do we turn that into a probability? We have another function, which is written here, a sigma of x. So this function turns an x between infinity to infinity into something between 0 and 1. Okay? So this function is called a sigmoid function. Right? We just give it a name. But this function is another exponential function, okay, to do the mapping. All right, so if we turn x, a score, right? If we turn a score into a sigmoid form, it turns out that this is between 0 and 1, all right? The original score, when the original score x is 0, this sigmoid x is 0.5, okay? So the midway is the same, all right? When the original x is above 0, this sigmoid x is above 0.5, okay? Vice versa. So when we turn this from infinity to infinity score into a sigmoid version, then the domain, okay, the range is 0 and 1, and the division point is 0.5, okay? When sigmoid x is more than 0.5, it's a positive class. Otherwise, it's a negative class. All right. So we take the probability of y equal positive 1 as sigmoid of theta dot phi x. Okay? As a result, the probability of y equal minus 1 will be 1 minus sigmoid theta dot phi x. Okay? So this is a version for binary classification. Okay. So let's make a summary. Our modeling target is py given x, okay, for text classification. And how do we parameterize this model? All right. So we first, okay, map the input or the input-output pair into a feature representation, okay? And then we define a model parameter vector theta. We use theta dot phi to define the score of outputs, all right? For binary classification, the feature is phi x only, and theta dot phi goes through a sigmoid function to calculate probability of y equal plus 1. For multi-class classification, we extract the feature vector from x and y pairs, all right? And the theta dot phi goes through a softmax function to calculate the probability of each y. That's clear, right? So, but hold on. We only got the modeling target and parameterization. We don't know how, given a set of training data, we can learn the values of the parameter so that these something between 0 and 1 is really a probability, right? So now it only looks like a probability. We're not sure it's a real probability. The problem is, how do we train this model? Okay, so let's take the binary classification case as the running case. How do we train a probability model? Of course, you need a set of training data, and this will be the same as naive Bayes classifier. Imagine that you have a data set with labels, right? You have already manually labeled your data set. So no matter how many instances you have, say that is n, capital N, right? 500, 5,000, 50,000. And every instance has an input, which is a text, and an output, which is a class label, right? You want to extract knowledge from this data set and distill that into your log linear model, right? So that's the training. How do we train a probability model? week 3, we learned a technology called maximum likelihood estimation, right? So the idea is the model can give a probability to every training instance, right? As long as I have an x and y, right? We have phi xy, right? And that dot, our theta is the probability, right? Going through a sigmoid or softmax. So, you know, when you're given a training instance, you got the model score. And all the model scores, when accumulated together, becomes the data likelihood, right? So maximum likelihood estimation says you just want to find the set of model parameters that maximizes this data likelihood, right? And you distill knowledge into your parameters. So that's MLE. Okay, so what is the data likelihood? It's written in this slide. So it's a conditional probability, right? This is the first time we see conditional probability as a likelihood, right? So week 3, we're tossing coins, we're casting dice, we're drawing words. Those are non-conditional probabilities. An IE base is a joint probability as well. Conditional likelihood is basically the same as the unconditional likelihood. You just multiply the conditional probabilities together, assuming that they are IID training instances, and this is the data likelihood. And we can spell out this likelihood using our parameterized model, right? We just replace py given x using our model parameterized function, the scoring function. What's the scoring function? Well, if you assume that we're doing binary classification, you extract phi x to represent x. You use theta to dot that phi x. And we learned that for y equal 1, right, it's sigmoid theta dot phi. For y equal minus 1 is 1 minus sigmoid theta dot phi. So we need to differentiate them, okay? So data likelihood is a product of every training instance probability. So we split them into x plus and x minus. Or if I index every x with I, so I separate them into I plus and I minus. So all those plus things correspond to a golden label of y equal plus 1, and vice versa. So those probability will be the product of two terms, right? One term is the sum of all positive instance probabilities. The other term is the sum of, not sum, the product of all negative instance probabilities. And then we further turn this probability into a logarithm of the probabilities. And then you got two sums, you know. If you see the equation here, the logarithm of the data likelihood will be the sum of all possible instance probabilities, logarithm, right? Plus the sum of all negative instance probabilities, logarithm. All right. You just replace them with the sigmoid and 1 minus sigmoid. You got the equation like this, okay? That's the data likelihood. And our model parameters in it, right? Now what we want to do is we want to maximize this function and find the value of theta, right? How do we do that? Our objective function is written here, one equation, okay? And we want to change theta to find its optimal point. So why don't we just take the gradient, right? So for week 3, we used to take the gradient, and we used to find the analytical solution. Now we just take the gradient. Many steps, okay? So these steps are obvious to some of you, not so obvious to others. Why don't I just take the most difficult part. Okay, let's take logarithm of 1 plus e to the power of theta phi x. Okay, for example, right, this is the most difficult term, right? So theta dot phi, the derivative with theta is what? Is phi, right? It's not difficult. But this part can be a little bit difficult, right? So, but for calculus, you know, so you take this derivative with theta. How do you do that? How do you do that? So it's a derivative chain rule, right? Yeah, you first take the derivative of this thing with respect to the logarithm, okay? And that's equal to this something, 1 over this something, right? 1 over this something, right? And then you take the derivative of this thing with respect to theta, right? So this thing with respect to theta, what is it? So 1, constant has 0, right? Gradient. And this thing, e to the power of something over theta. And then chain rule again, right? E to the power with respect to theta is equal to e to the power of this thing itself, right? And times this thing with respect to theta, right? And this thing, if I take the derivative, it will become phi x. All right? So that's the process for the difficult part. Oh, this looks very difficult. It's a complex equation, but wait. So this thing over this thing, what is it? What is this function? Sigmoid, right? So, and that's equal to the probability of y equals plus 1 given x times phi x. Oh, this looks very simple. Okay, and this is how we got the result. All right. But the problem is that even if this thing is very simple, okay, the equation we got here at the end of the slide is still difficult to optimize, right? Because we have a large data set, and for every training instance, you have a probability. Obviously, there is no closed form answer. All right, I have the gradient, but I cannot make the gradient 0, okay, to solve the equation. So what can we do? So we need to turn into a numerical solution, all right? So let's recap. So I have a training objective function, maximize the likelihood, right? And I know the derivative of this thing with respect to the model parameter. And now I want to find the maximum point of this function. I can do that by starting from a random model parameter and then gradually adjusting it. Okay, a numerical solution is called gradient descent. It calculates the minimum point of a function, but nevertheless, if we take the negative log likelihood, okay, the minimum of the negative is the maximum of the positive, right? So it doesn't really matter whether we do gradient descent or gradient ascent. There's a deeper reason why do we want to do gradient descent, okay? We will see that later, but let's just assume we're doing gradient descent over the negative log likelihood. So how do we do that? You know, there's not necessarily a closed form solution, but you can do it gradually. Suppose, okay, we're on a mountain, So we want to climb down the mountain to a minimum point. Okay, so in this situation, our GPS location is the theta. Right? We can move left to right, okay, or in any direction. Okay, that's the theta, and our altitude is the objective function. Okay, negative log likelihood, right? So how do we find a negative point? So we can start off from anywhere on the mountain, okay? Any GPS location. And at this location, we can look at, okay, which direction is the steepest slope downward, okay? Of course, if you move towards some direction, you climb up, right, over GPS. You move over other directions, you go down, all right? So how do we know which is the steepest direction? Okay, it turns out that the gradient of this altitude over your GPS location, XY, is the direction, okay? Is the direction up, right? And you take the negative of this gradient, you can climb down. All right, now we know the direction, right? We know the angle, where to go. Now we have x, y, right? We know the angle. But the next thing is, how much do we need to go down, right? You know, the gradient has a value. The gradient has a value. So we can multiply this gradient value with a step size. Let's say alpha, right? Alpha could be 0.1, 0.001, or 100, I don't know. But this is called a step size, okay? We multiply this alpha to the gradient, and we make a move on the xy coordinate, right? And then our altitude will change correspondingly. Okay. Now after one step, we got a new xy. I'm pretty sure if the step size is small enough, this new xy will be lower than the original xy, right? Because we're climbing down over the negative gradient direction. So in this new location, we need to look at the environment again, right? And find a new slope downwards. So that's a new gradient. Okay, and we take the same step size and go down again. So we're moving on the GPS XY, and we're changing the altitude, okay? Until when? Until we no longer go further down, until we reach a valley, okay? The bottom of a valley, and we're done. Okay, so that's a local minimum, right? We're not sure about the global minimum, but we're sure that we can reach the local minimum. That's the idea of gradient descent. So if I describe this thing using an algorithm, it's very easy, okay? So we just initialize this theta using a random vector, okay? And then we can calculate the objective function, right? We can calculate the gradient of this thing over theta, okay? By putting theta in, and we got something like this, okay? And then we just take the gradient as a step, and we multiply the gradient with alpha, and we just go on the negative direction of this thing with alpha g. G is the gradient. And we repeat this until what? Until my next model parameter and my previous model parameter don't change a lot, you know. It means we reach the bottom of a valley. And we can stop. And that's the local minimum. So the learning rate, the step size is called a learning rate. It's a hyperparameter. Okay, we can tune that on the development data. Okay, and just as I said, if we just go down slope, we can guarantee to go to a local minimum of this function. All right. But there's a problem. The problem is if our data set is large, then calculating the gradient over the data is computationally inefficient, right? So suppose we're training large language models. We'll discuss this later. And we have 200 billion words, okay? Oh, we need to calculate the gradient of the model over this huge corpus. It's very inefficient, all right? What we want to do is we want to change the model parameters quicker. So how do we tweak this algorithm? We can do that by not changing the model parameters after every iteration over the data, okay? We can go changing the model parameters after every instance. We change it a little bit. And that's called stochastic gradient descent. So the difference between SGD and GD, okay, is just one thing. It's just the loop variable, okay? So originally we loop over the whole data set and calculate a gradient at each step, okay? Now we loop over all the training instances, okay? So for every training instance, we know its probability, right? So when all the probabilities add together, log probability add together, it's the data likelihood. But for every instance, we have a local log probability according to the model, right? That's sigmoid theta dot phi. So we can take the gradient, local gradient, over this instance, training instance. That's what's written in this pseudocode. For I is equal to 1 until n, capital N, I go through all the training instances. I have x, y, xi, and yi, right? So we calculate this, the gradient over xi and yi, and I use this gradient multiplied by alpha, the learning rate, and I update theta. Okay, so I go down the slope quicker. Okay, instance by instance. Okay, so I just check one instance, I go down. Check another instance, go down. Check another instance, go down. Okay. Now this time we don't measure whether our model converges or not. We just say we can iterate over all the training data for t iterations, capital T. That's another hyperparameter. Okay. And we can do the same. Oh, this is a little bit similar to something we learned last week, right? Some of you remember, some of you don't quite remember. Okay. But we just go through all the training instances for t iterations, right? For every training instance, we do some update to our model parameter. So if we replace this gradient with the gradient for our log linear model. Okay, the gradient for the log linear model is written on the right. I calculate that for every instance, right? For positive instances, the gradient is 1 minus, okay, py plus 1, okay, py equal plus 1, times phi. For negative instances, the gradient is py equal plus 1 times phi x, okay? So when we plug this into SGD, you get an algorithm on the left. So for every training instance, I just calculate the probability of y equal plus 1 according to the model, right? So sigmoid function. And if the goal y is plus 1, then I just use 1 minus this probability times phi x as the update, okay? Of course, we have a learning rate. And if the instance is a negative 1, we just use, okay, p, y equals plus 1, or the sigmoid version, times phi x, okay? So this algorithm is similar to something we learned last week, but I'll go to that later, okay? So that's the training process for log linear model, okay? So now we finished the log linear model. We learned the parameterization, we learned how to train that using data, right? Using this algorithm. SGD is an approximation of gradient descent, okay? It often gives a strong result compared to GD. But there is a compromise between GD and SGD, which is called mini batch SGD. And the idea is also very simple. So SGD approximates GD by doing update after every one simple instance, right? GD updates after calculating the gradient over the whole data set. So mini batch SGD is something in between. So we don't calculate the gradient over one instance. We don't calculate the gradient over all instances, but we calculate the gradient over a batch of instances, okay? So maybe we have a batch of 100 instances for one gradient. So the batch size will be 100. Maybe we have a batch of 1,000 instances for calculating the gradient and then updating the parameter once. So the batch size will be 1,000, all right? Okay. So this is pseudocode of mini batch SGD. It's slightly different from original SGD by grouping our instances into batches and calculating the gradient by accumulating them over the whole batch and then before making an update to the model parameter. Okay, I don't have time to go through it. So let me just move on to the training of multi-class log linear models. Okay. So for multi-class classification, we have the parameterization over a softmax function. Okay, so this is how the model calculates the probability. And then we can train the model in the same way as binary case. We calculate the data likelihood, all right, log likelihood, which is in the second equation here. And then for every training example, you just remove the summation. The likelihood will be, log likelihood will be this. Theta phi minus log, the sum of all possible labels, e to the power of theta phi, that class, okay? How do you calculate the gradient? I leave it to you to do it offline, referring to the textbook, but the gradient will be, okay, phi xy, which is the feature vector of the gold instance, minus phi xc, okay, the feature vector of one incorrect instance, okay, c, okay, times the probability of that c given x. And then this thing summed over all incorrect c's, okay. That's the conclusion. So if I replace that into the log linear model, we arrive something like this, okay? So I just replace that gradient. The gradient is written on the bottom of this slide, okay? I plug this into SGD. I got a training algorithm for multi-class log linear model. So basically, I randomly initialize my model parameter, and I go through all the training instances for t iterations. For every training instance, okay, I calculate the probability of every possible output label. And then I use the gold feature vector minus this feature vector, okay, times the probability of this class label as the parameter update. And I use alpha as the learning rate, as written in this pseudocode. All right, and that's how to train the model. Okay, let me make a summary. The log linear models, all right, the modeling target is the probability of the class label given input text. The parameterization is sigmoid or softmax over theta dot phi. the training is maximum likelihood estimation. And the training process is defined by using SGD or mini batch SGD over the training objective. Okay? How about testing? For testing, we're given an input, and we can use the trained model parameters to calculate the probability for all possible Y, all possible class labels. And we just select the most probable one. Okay? And there's a side remark. So in other textbooks, binary classification log linear model is called a logistic regression. Okay? So maybe you have a different perspective of logistic regression, which you learned in the machine learning. But because both softmax and sigmoid are monotonic functions, finding the maximum of sigmoid theta dot phi is the same as finding the maximum of theta dot phi. And as a result, the testing scenario for log linear models are exactly the same as the testing scenario for perceptrons and SVMs. So after we learned log linear models, I want to come back and answer the question, okay? The training algorithm for log linear model is very similar to something we learned last week. What was it? Okay? Well, some of you already got it. The answer is perceptron. In fact, last week, we only learned one training algorithm, which is the perceptron algorithm, right? We learned SVM, but I didn't show you how to train it. How did perceptron train? So I just put together logistic regression and perceptron for binary classification. And you will find that they are very similar. Okay? Both of them initialize the parameter vectors into a random vector. Oh, wait. The perceptron initializes the parameters to all zeros. But I just said with SGD, you do random initialization. But you could do the same for log linear models by initializing theta to all zeros. What's the advantage? The advantage is that with the fixed initial value, so every time you train the model, you get the same model, right? Because gradient descent, the convergence depends on the initial position, right? If you stand close to a global minimum, then you can climb down to the global minimum. If you stand in a local minimum that's not the global, then you don't converge to the global one. So, but if I initialize the model parameter to all zeros, I can make my model training reproducible then. Okay, so if I both initialize the model parameter to all zeros, then perceptron and log linear model logistic regression, they both go through all the training instances over t iterations. This is similar, right? And then for every training instance, they calculate the score of a positive sample and negative sample through theta dot phi. Okay, so this is another similarity, but the difference is that okay, one more similarity. Okay, so if you look at the parameter update, they both update theta using what? Using phi, right? So every time they do the parameter update, they do it over different training instances, right? So perceptron updates theta using phi every time you add a phi to theta, right? The log linear model, every time you also update theta using phi. This is the third similarity. Now let's talk about the differences. The first difference is here. The perceptron does the update using a condition, right? As I said, if the model update is, if the model prediction is correct, I don't update my model parameters. If the model prediction is incorrect, then I update my model parameters, right? So if the gold label is positive, I just add phi to theta. If the gold label is negative, then I subtract phi from theta, right? Okay, this is perceptron. For log linear model, it's slightly different. It's like, no matter whether my prediction is correct or not, I will do the update, right? So for the positive samples, how do I update? I update my model parameters by adding something times my theta, my phi, okay, to theta, right? What is this something? This something is a weight, right? So basically, I weigh my phi and add that to theta. What's the weight? The weight is 1 minus py plus positive 1. Of course, there's a learning rate, alpha. Let's forget about the learning rate. Why do I need to weigh my phi? Think about it. So I always add phi to theta unless the probability of my positive sample is 1, right? If the probability of the positive sample is 1, then 1 minus 1 is 0. I don't update my model parameter. But as soon as it's less than 1, then I update my parameter using 1 minus this probability. What does it mean? It means that the lower the model gives a positive sample, a positive probability, the more aggressive I update my model parameter, right? Right. That means I require my positive sample to be scored 1 probability, okay? If it is closer than 1, then okay, I give it smaller update. But if it's closer than 0, I give it a big update. I want it to be 1. So that's what I think. For negative instances, the update is to subtract phi from theta, right? This is similar to perceptron. But perceptron says, if you don't do it correctly, I will update my theta using the whole phi, okay? But logistic regression says, I will always subtract phi from theta unless you give it a 0 probability, right? You give it a 0 positive probability, I don't update it. Otherwise, as soon as you give it a small probability, okay, I just use this probability to weigh my phi and subtract the phi from theta. That's also understandable, right? Because you want the negative instance to receive 0 positive probability. And the higher the probability is, the more aggressive the update is. Now, when I forget about the learning rate, this difference leads to the difference between the perceptron score and the log linear model score, okay? And that results in a log linear model calculating a probability, right? So you can understand that from this algorithm. And this is for multi-class classification. Okay, multi-class. So on the left is log linear model. On the right is perceptron. So again, you see a sheer difference. Okay, let's first talk about the similarity. They both initialize the parameter vectors to zeros and go through all the training instances for t iterations. And every time it uses phi xc to update my theta. That's the similarity, okay? The difference is that perceptron does the update according to a condition. What's the condition? If the model output is incorrect, right? I just add the correct output phi to theta and subtract the incorrect output phi from theta. That's perceptron update. But log linear model does what? It considers all possible outputs, you know? And for each output, it calculates the probability of this output. Right? And it weighs the update by using the probability to multiply the gold feature phi minus this current output feature phi. Okay? You can understand it as if the gold output has a probability of 1 and all the incorrect output has probability of 0, then it doesn't do the update. Otherwise, as soon as log linear model gives a small probability to any incorrect sample, it will do the update. Okay? And the update is the feature difference between the gold sample and the incorrect sample, weighted by the probability of that incorrect sample. All right. And that leads to the result of a probability score. Okay, so I guess that gives you some another view, okay, of the training of log linear models. Now let's move on. So last week we learned SVM, but I didn't tell you how to train them. What is SVM? SVM is basically an algorithm that separates correct and incorrect samples by finding a margin, right, in a vector space. And this margin is represented by a half of theta square, right, as we learned last week. So a half of theta square decides, okay, how far are the support vectors to the hyperplane. But there was another term, which is the violation we discussed last week at the end of the class, right? So it's a sum of all instances, max of 0 and 1 minus y theta dot phi. If you remember, so if this theta dot phi, right, is always higher than 1 on the positive side and lower than -1 on the negative side, then there's no violation. Which means that they're all further than support vectors, right? But as soon as some vectors that they sit between two sides of support vectors, then there's a violation, right? The violation is between 0 and 1. But even more severely, if it sits on the other side of the hyperplane, then the violation is more than 1. So this is what the equation says, okay? In the end, our training objective of SVM is to minimize the half of theta square, the margin, okay? Maximizing the margin, plus the sum of all the violations. That's a new training objective. It is an unconditioned optimization algorithm, okay? So I use the term C to weigh between the violation and the margin, right? So that's the training objective. But I can also turn that C into 1 over lambda, and I got this equation in the middle of the slide. That's a new training objective, which is the same, Okay, it's just that I put the term on the margin. Rather, I put the weight on the violation. Why do I do this? I tell you the reason later, okay? But I tell you that these two objectives are equivalent, obviously, right? No need for proof. Okay, so this is the training objective, but how do we optimize it, okay? So just to recall, I have the parameterization, I have the training objective, but I need to turn the data into my model parameter. That's the training, right? Okay, but now we have a general algorithm called SGD. SGD can be used to optimize everything. Okay, so why don't we put this training objective into stochastic gradient descent? Then what do we need? What do we need? We need the gradient of this thing over theta, right? As long as we have the gradient of the training objective over my model parameters, I can plug this into the SGD framework. I got a training algorithm, right? So all I need to do is to calculate the gradient of this thing over theta. But you know, this thing has a max on it. And you learn in calculus that max of something is non-differentiable. It's not a continuous function, not smooth, right? So how do I calculate the gradient? The thing is, I can take the two halves, you know. One is when the max is 0, right? The other is when the max is non-zero. I can calculate the gradient on each half. That's called subgradients, right? So let's do it. And I show that on the equation. When this max term is 0, it's a constant, there's no gradient, then the whole gradient is over that a half of lambda theta square, right? You take that with respect to theta, you got what? The gradient is lambda times theta, right? No need to think. Right? But if this thing is not 0, then the thing becomes y dot theta, the thing becomes minus y times theta dot phi, right? Within that max, when it's more than 0. And then calculating the gradient with respect to theta is also easy, okay? It's minus y phi, right? When you calculate the gradient of that thing, it's minus y phi. All right, no brainer, right? Okay, so the two subgradients are here. So when y theta phi is larger than 1, the gradient is lambda theta. Otherwise, the gradient is lambda theta minus the thing, okay? Okay, now all I want to do is I just plug this, you know, this gradient for every training example back into SGD, right? And I got a full training algorithm for SVM. On the left is SGD, on the right is the training version for SVM. How do I train SVM? My model parameter is theta, right? I initialize theta to all zeros. And I go through my training data for t iterations. So when I look at every training sample, what do? I check the model score. Y theta phi, is it greater or equal to 1? Okay. Y dot theta phi, is it greater or equal to 1? What do I mean? I repeat this. So theta dot phi is the model score, okay? When y is positive 1, which means for a positive data instance, if the gold label is positive, I want to check whether theta dot phi is greater or equal to 1, right? So when the gold label is negative, when this is a negative training instance, I want to check whether theta dot phi is smaller than negative 1, right? If the positive sample score is more than 1, the negative sample is smaller than negative 1, then I don't have any violation, right? The example sits beyond my support vector, you know? No update. Otherwise, I know y theta phi is smaller than 1, I need to do the update. What is the update? The update is theta is equal to theta plus y dot phi. You know, gradient descent, right? I minus the gradient. So theta is equal to theta plus y dot phi. What does that mean? It means that for positive samples, I train SVM by adding phi to theta, right? For negative samples, I train SVM by subtracting phi from theta. That's what it says. Oh, this is very similar to perceptron, some of you found, right? And then, no matter whether it's positive or negative, you do this theta is equal to theta minus alpha lambda theta. What is this? This is the gradient for the margin, right? And that's it. That's the training for SVM. So after you use this algorithm over your training data, you get an SVM. Right. So this is for multi-class classification. It's very similar. The objective for multi-class classification also has two terms. One is the score margin, a half of theta square, right? One is the violation. I want the gold output score to be higher than any incorrect output by a margin of 1, you remember, right? So, and then 1 minus the negative score plus the gold score is the violation, right? If this violation is greater than 0, then I want to minimize this violation. But if the violation is smaller than 0, there's no violation. I just take it as 0. Right? This is what we learned last week. So I have a C term to weigh the margin and the violation. If I turn this C into 1 over lambda, you know, I got an equivalent training objective. Obviously, maximizing the first equation is the same as maximizing the second equation. Right? Okay, sorry, minimizing. And then all we want to do, okay, is to use SGD to train theta, all right? And to use SGD to train theta, all I need is the gradient of this objective over theta, right? What's the gradient? The gradient is like this. It's subgradients. It's subgradients. So when there is no violation, you know the violation term is 0. So I only have the gradient for the margin term, right? So it's lambda theta is the gradient of the margin term. But if there's violation, I need to add the violation gradient over the margin gradient. So the violation is phi xy minus phi xz, where z is the model output, okay, which is the class label that has the highest score, okay. Argmax c n equal to y theta dot phi xc. Argmax is the argument that gives the maximum to the function. Now I got this subgradient. I plug this into SGD, and I arrive at a training algorithm for multi-class SVM. Okay, I will just repeat myself. Okay, how do I train SVM? You know the parameterization is theta dot phi xc. Okay, and to train this using a set of data, I first initialize theta to all zeros. And then I use the current model or current theta to go over all my training instances for t iterations. In any iteration for xi and yi, what do? I first calculate the model output or the class label z that has the highest model score, theta dot phi. Okay? And then I will decide, does this z has a lower score? Okay, if this z is equal to the gold output, then we're fine. We don't do any update, right? But if this z is not my gold output, then we have a violation. Oh no! Even if this z is scored lower than the gold output, I want the score to be lower than the gold output score by at least 1, right? Right. So if the gold output is my z, then we're fine. But if the gold output is not z, okay, we're not fine, okay? No, even if we are fine only when the gold output is higher scored than the highest scored incorrect output by at least 1. So that's what I mean, okay? If we don't satisfy this score margin, then we need to do an update. The update is to use, okay, the gold feature vector phi xy minus this z, the highest scored incorrect output, okay, phi xz as the gradient. And then we use this alpha g plus alpha lambda theta to update my model parameters, okay? All right, sorry, I just made a small confusion to you. Now let's, in order not to confuse some of you, let me repeat. This z is not the highest scored output according to my model, but the highest scored incorrect output according to my model, okay? If the output is correct, we're fine. But we want to find the argmax z not equal to yi, right? We want to find the highest scored incorrect sample. And if the score of that one is not smaller than the score of the gold sample by 1, I do this update, okay? That's the condition for SVM. Okay, now again, this is very similar to perceptron. Now why don't we make a comparison between perceptron and SVM? And here it is for binary classification. Okay, so both algorithms will find a condition to update my model parameter. So when the condition is satisfied, both use y dot phi x to update my model parameter. It's just SVM has a learning rate alpha, but we can forget about the learning rate, okay? So the difference between SVM and the perceptron only lies in the condition. SVM requires correct samples to be scored by more than 1, incorrect samples to be scored by less than -1, right? Okay, but perceptron is more generous. Perceptron requires that as long as my model output is correct, it requires the gold to be scored more than 0, the incorrect one to be scored less than 0. Okay, so the condition of SVM is more strict. Now the second difference is that SVM has a margin term, So SVM will always subtract lambda theta from theta. But perceptron doesn't have that. Okay, this is the difference between binary case. For multi-class case, it's similar, okay? Both algorithms run through the training instance by t iterations, and both uses the gold feature vector minus an incorrect feature vector to update the model parameter, okay? SVM has a learning rate in addition, but the condition is different. Perceptron looks at the gold and the model output. As long as the model output is not the gold, it does the update. But SVM looks at the gold and the highest scored non-gold example. Okay, it requires the gold and highest scored non-gold to have a score margin of more than 1. Otherwise, it will update the model parameter using the tool. All right. The second difference is that SVM always subtracts lambda theta from theta. So it's the margin term. All right. So if you really compare the perceptron and SVM, because they're so similar, you can back engineer a training objective function for the perceptron. Okay? If my perceptron were some training objective trained using SGD, then what should it be? You can reverse engineer, right? Reverse engineer. It turns out that the perceptron training objective is written in the second last equation. The sum over all training instances, max of 0 and this max c theta phi xc minus theta phi xy. So if the score of the gold, okay, is less than the score of an incorrect one, I do the update, right? And the gradient is the difference between the gold and the incorrect one. Otherwise, I just pass on. Okay, this is what I reverse engineer. How do you verify that? You just take the gradient of this thing, right, and plug into SGD. You find this is exactly the same as the perceptron. All right. So we're done. Let's recap. What did we learn so far? Okay. I just shared with you two things. One is a log linear model, right? I defined a log linear model training objective. And one is SGD. It's some powerful tool which you use to train every model. As long as you have a training objective, you can use SGD to find the weights, right? And then using SGD, I compared the log linear model, SVM, and perceptron, and I find, ooh, they are so similar. They only have subtle differences, right? They only have subtle differences, but they are all like an iterative online learning process. Okay? So that leads me to think, okay, could they be just different instances of the same thing, right? We've learned 3 different machine learning algorithms for text classification, but could they be the same thing? Okay, first let's look at where they are the same. The model form can be identical. All of these models calculate the score of y given x, okay? This is what we learned in second week, right? The scoring function is what? Is f of theta dot phi. For SVM and perceptron, this f is identical function, identity, right? Or no function. For log linear models, this f is sigmoid or softmax. Okay? So this is the similarity. And the test scenario is also the same. Test scenario is the same as what we learned in week 2, right? So you're given an x, you want to enumerate all possible y, right? You calculate the highest score, or theta dot phi. You just need to find the y that has the highest theta dot phi. Test scenario is also the same. Training is different, but let's look at training later. Although training is different, but the training is also under the same process. So every algorithm can be illustrated like this, okay, like this. What do I mean? I mean, I turned my input into a vector, right? That's called the representation, right? I turned my input into a vector. And in the end, I pass this vector into a theta, that model parameter theta, right? And I calculated an f of theta dot phi, okay? So for binary classification, this f is a sigmoid function, okay? So when this thing is more than 0.5, you can think about the output as being activated, okay? It's closer than 1, right? A sigmoid is an exponential function. When it's smaller than 0.5, you can think about this thing as not activated, but this thing is closer than 0. Okay? All right. So this thing is very similar to a neuron in biology. Biologists have found that some of the neurons, okay, work in this way. So you have many neurons that are connected to the neuron, okay? These are connections. And if the input, okay, is strong enough, you know, to pass over a threshold, the neuron will send an electric signal out. So this is called the neuron activation. And this F function that calculates the output, okay, you know, sigmoid goes like this, okay. Sorry, I didn't draw it in my slide, but I will compensate you by drawing it here. So sigmoid function x is minus infinity to positive infinity, and this is 0, this is 1. The sigmoid will be something like this, okay? Something like this, all right? So it doesn't stay close to 0.5 for much range. So this is like activation. So as a result, this sigmoid function is called an activation function, right? And we call this a neuron. A neuron. So a neuron will take an input vector, okay? And then the neuron itself has a theta, you know, the theta is a set of weights that are dot producted to the input vector, okay? How can I visualize this theta? This is like the arcs here. So every theta is assigned to one arc, okay? So phi 1, so first feature, times the first theta goes through this neuron, right? Second feature times the second parameter go into the neuron. So the higher the theta value is, the stronger this neuron is connected to the input neuron, you can think about, right? And in the end, accumulate these signals in, and I pass them through an activation function to calculate the output. Either activated or not, right? Okay. This is like a neuron. But then you say, for multi-class classification, it's a slightly different, right? For multi-class classification, of course, you can write the multi-class classification like this. It's just that the phi, the representation vector, becomes x and c, right? And then you pass this representation of input-output to a neuron, and then you get the output score, right? You pass the different vectors into the same neuron, you get different scores. You can think about it like this. But I'm saying I can turn this thing into another structure. It's like I don't want to put my phi xc on the left, okay? I want to put my phi x on the left. And then I calculate a c for every class label. That's also possible as a multi-class neuron. Okay, but then you say, wait, this is different from what we learned last week, right? Last week we learned phi xc is the representation, okay? That to a theta is the score of c, okay? Now you say, can I map this thing to phi x is the representation, okay? And then I have capital C neurons, as many neurons as my class labels, okay? And I calculate a score for every class label here. Is that possible? So I show you here in this equation, okay, in the bottom side, that phi xc times theta is equal to phi x times some theta c1, theta c2, theta until theta cc. How do you understand it? I'm just using one example, right? Let's suppose I only have two feature templates, C and WC. Right. If you have these two feature templates, then your feature vector phi xc will be written like this. You are very familiar already, right? So it's C rows. For every row, you combine one class label with one, W1, W2, until WV, all the words. All right. So, and then what we had was to use this phi to dot product theta to get a score for C. All right. Now, let's rename this thing a little bit. First, let's rename every row in my theta, okay, as theta C1, theta C2, until theta CC. Can we do that? So I cut this whole theta vector into C components, right? Each component corresponds to one class label. I can do that, right? So in the end, my whole theta vector will be the concatenation of all these small chunks, right? Each chunk is just one row. All right, I cut my big theta, and you see, this shows us this theta will be the concatenation of every row. I just cut it, nothing else, okay? How about my phi xc? You know, I can think about phi x as 1, W1, W2, W3 until WV, right? That pattern repeats in my phi xc for C rows, okay? In every row, it's combined with a particular C, right? Okay, so my phi xc can also be cut into C chunks, okay? For every chunk, it's the multiplication of phi x to what? To a Kronecker delta function. This delta C1, what does it mean? This delta C1 is equal to 1 if C is equal to C1 and 0 otherwise. Okay? So if phi x is multiplied by delta CC1, it exactly means the first row, right? When the C is C1, then only the first row is non-zero, and only those with the words in the document are non-zero. Similar for the remaining class labels. All right, so essentially, I cut my phi xc, right, into C chunks, and I cut my theta into C chunks, and you can easily prove that this phi xc times big theta is equal to phi x times the small theta over the Cth row. Okay? For every possible C value. So once you see that, you can turn this into the second form. I put phi x on the left, right? And I put each theta c into a neuron. C different neurons, right? So that's a multi-class classification way. Why do I do that? I'm actually preparing you for learning multi-layer perceptrons, okay? So I'm just saying that these two formulas are equal. Okay. Now this is the testing case, okay? This is a testing case. All I'm trying to do is to find the representation and then calculate a score, okay? No matter whether I represent the input or I represent the input and output. All right. And I just said the training algorithm for the three are similar too, right? If you carefully look at the training algorithms, you can summarize them into this thing. No matter whether it's SVM or other algorithm, the training is to initialize the parameter to zeros and iterate through all the training instances, okay? For every instance, I use a pseudocode called parameter update, okay? So to update my parameter vector, all the three algorithms will be the same, right? You have to agree with me, right? It's just how you update the parameters differ. But this is just SGD, right? Okay. So how they differ? So for binary classification, I summarize the parameter updates. You can look at them again. So perceptron, SVM, and log linear models. The first two have conditions. The third one is unconditioned. Similarly, for multi-class classification, okay, I summarize the parameter update into this form. Okay. All right. And these, the difference between the parameter update roots, okay, in the difference between the training objective functions, right? Using SGD, they all minimize something. What do they minimize? I call the things they minimize as loss functions. Okay, I just call them loss functions. So again, I summarize this to you. On the left-hand side is the gradient. On the right-hand side, it's the training objective function, right? The training objective function decides the gradient and decides the parameter update. Okay. For perceptron and SVM, it's something like a violation-based objective function. For log linear model, it's just a negative log likelihood. Okay. All right. I can draw these loss functions into a picture. The picture is shown here. Different lines shows different models. Okay, the x-axis is the score theta dot phi. Okay, the y-axis is the loss function. Okay, I draw this for binary classification. You know, for binary classification, the higher the model score is, the less the loss function is, right? For SVM, you remember when theta dot phi is greater than 1, the loss function is 0, right? When theta dot phi is less than 1, the loss function is theta dot phi. So it's this line. It's the red line. Okay? When theta dot phi is greater than 1, no loss. When theta dot phi is smaller than 1, the loss is 1 minus theta dot phi. For perceptron, right? As long as theta dot phi is greater than 0, there's no loss, right? The model predicts the correct label. But when theta dot phi is smaller than 0, perceptron has a loss that is proportional to theta dot phi. Okay? So these two loss functions, they are these curves. Okay? They have a point of turning to 0. And they are called hinge loss functions. Right? For log linear model, the loss is what? The loss is a negative of the sigmoid function, right? Okay, but I take the logarithm, of course. The negative log likelihood. So it's something like, it's never 0, okay? But the higher this theta dot phi is, the lower this curve is. It tends to 0. All right? So these are the laws. But no matter what the loss is, okay, they're the same as the higher the score is, the lower the loss is. All right. I just turned the loss functions in this table into this picture. Okay. So this is just a visualization of these functions. All right. Okay. So that's easy to understand because as we learned in week 2, I want to assign high scores to correct samples, low scores to incorrect samples, right? But why do we have these loss functions? Can we just have an absolute loss function? What is it? So, you know we're doing binary classification, right? So if theta phi is greater than 0, I don't have a loss. If theta dot phi is lower than 0, I have a loss of 1. You know, this is called 0, 1 loss. Okay, this is conceptually easy, right? If I make a mistake, I have a 1 loss. All right? If I don't make a mistake, I have a 0 loss. So it's this shape, Z-shaped loss function. Can you use the Z-shaped loss functions to define a model as the training objective? I create a new model, right? Can you? It turns out that you can't. Why? Because this function is not differentiable to theta. Right? If I take the gradient of this thing with respect to theta, it's always 0. So it will be very difficult for you to optimize this loss function by using SGD, at least. All right. So, all right. What did I say? I said you can define different functions, okay, that grow towards 0 when the model score is larger, and grow towards high values when the model score is smaller. All right. So basically, the idea is you want the model to assign high score to positive samples. And actually, these loss functions reflect something called a risk. A risk. What is a risk? A risk is the chance that your model makes an error over arbitrary data. This is called a risk. Okay? The loss functions are ways for you to calculate these risks. All right? If for positive samples your model assigns a very small score, then you have a high risk of making mistakes, right? All right. So when you define this risk, then you can't help thinking about what is the ultimate goal of training. The ultimate goal of training any model, right, is to minimize the expected risk on arbitrary data. Suppose you can enumerate all possible x and y's, okay? Then you can calculate a loss on all these x and y's, right? You can calculate the mathematical expectation over all of them. If you are able to minimize this, then your model will not basically make mistakes on any data. But is that feasible? At least for text classification, it's not feasible because you can't enumerate all possible input documents, right? As a compromise, you minimize empirical risk. What is that risk? It's the sum of all loss functions over your training set. If you can't minimize the loss over everything, right? You minimize your loss over a set of training data. You used minimizing the empirical risk to approximate reducing the expected risk over arbitrary data. That's how you train a model. Okay, that's a little bit machine learning philosophy. Okay. Now, as a final thing, let me have a remark on this minimizing a half of theta square. Okay. You know, for perceptron, you only minimize the violation. For SVM, you minimize the violation plus a half of theta squared. Okay, we had an interpretation of this over the vector space. I says, if I choose a margin, if you choose a separating hyperplane that has the largest margin, right, then you're safe on unseen data. But I can also give you a numerical interpretation, which is, suppose, okay, you have one element in theta that is as big as an elephant. Then what do? You will result in a very high theta square, right? If you have every element in your theta almost equally small value, okay? Not almost equally, but they are all moderately small value, then your theta square is low, right? You have to assume this. Why do you want the theta to be equal and not an outstanding value in theta? Because an outstanding value in theta will mean that your model will overly rely on one feature, right? If theta has a very high value in one element, then the corresponding feature will almost determine your class label. You don't want that. That easily leads to overfitting of your training data because we are not sure that any feature will generalize to all data. All right, so minimizing a half of theta square tries to regularize your theta a little bit, okay, to reduce the chance of any element of being large. As a result, this thing is called regularization, okay? And minimizing a half of theta square is called L2 regularization. And minimizing the theta norm is called L1 regularization. You can add regularization to your perceptron training algorithm, leading to SVM. You can also add regularization to your logistic regression or multi-class log linear models, okay? All right, so let me skip the multi-model stuff. I leave it to you to read offline, and let me make a summary. So in this week, we just learned a general linear model, okay, which is called a neuron. The neuron parameterization is an activation function plus this theta dot phi. And we have seen different ways to define loss functions, right, over a set of training data with negative log likelihood loss and violation loss. And we have also learned how to add a regularization term to your loss function. All right? With different loss functions being defined, you rediscover important machine learning algorithms in history. Perceptron, SVM, logistic regression, etc. They are all a neuron, okay? And then the second thing I informed you is that you can use a gradient descent algorithm to train all these different instances of the neuron, okay? So from next week, we will move on to word representation and some information theory. Okay, see you.